10. They're both going from the same height. So this height here, the same height that you're using here. The time in the air is what you're calculating here. So you can put that time here and here, right? Because it's going both horizontally and vertically. And then we're going to use our velocity is equal to displacement divided by time to give us our initial horizontal velocity that this thing is being launched with. So I say initial horizontal velocity because when it's projected in the air, this is the velocity as it's leaving the table. But we could also identify it as our final velocity if we are talking in terms of our conservation of momentum. I digress. Let's just be careful about what velocities we're using when. So my conservation of momentum statement, this is the mass of 1 and the velocity that I calculated here right before it hit mass 2. Mass 2 is at rest. It has no velocity, so it has no momentum. So the only thing giving our system some momentum before the collision is our marble that was down the ramp. And then we have our velocity and mass of our post-collision. So these velocities are coming from our t-charts here and our masses we measured at the beginning of the lab. When we look at energy, say if this is conserved, we're going to take the energy of our marble, right? We really use this energy here too. The energy of our marble 1. There's no energy of our marble 2. If we're talking in terms of the table being at ground level. And then post-collision, these are the velocities that we're getting from here as they first are entering into free fall. So this is 1 and 1 and 2 and 2. All right. Then for our extension, we're going to make some graphs. These graphs are going to be energy as it relates to time for both M1 and for M2. So I put our time in terms of t, from the time that it left the table until the time that it hit the ground. So we're going to do a quarter of that time. We're going to do half the time. We're going to do 3/4 the time, and then the time that it hits the ground. So from the time it leaves the table to the time it hits the ground, we are going to graph our energy for both marbles. Our gravitational potential energy will be one line, right? It's going to go down, and our kinetic energy is going to go up, right? Because our energy is conserved because we're neglecting air resistance. So both marbles will have gravitational potential energy and kinetic energy as they leave the table, and you need to identify how much of each they have, and I'll show you how to organize your data on the next page. We're also going to do a set of kinematics charts. I made a mistake here. We can delete that. So in the y direction, I only have one set of graphs for the y direction because they are still under the influence of gravity, and their heights and velocities and accelerations should be the same for both marbles. So I'm going to just have one set of graphs for that. In the vertical direction, our displacement is going to be negative. We're going from a higher position to a lower position. Our velocity is going to be 0 to begin with in the vertical, and then it'll be some other number when we reach the ground. And our acceleration, of course, is going to be -10. I'm also just made one for our horizontal acceleration, it being 0, right? There's no acceleration in the horizontal direction. All right. For M1, you've got your displacement in terms of time. So 1/2 time, 1/4 time, 3/4 time. And our velocity, right, we should have a constant velocity, so whatever value we calculated, we're just going to plot that value. It should be a horizontal slope because we have no acceleration. And we're going to do the same for M2. Our displacement from the time it leaves the table to the time it hits the floor, and our velocity from the time it leaves the table to the time it hits the floor. This is in the horizontal. So these two marbles will be going with different velocities, so their displacements will be different. You have their displacements because that's what we measure.